Okay, so as I mentioned in yesterday's lecture, the assignment is now up on LMS, and I just want to spend 5 or 10 minutes talking about the assignment to kind of prime you for that, okay? Particularly because next week you're going to start, or some of you are going to choose to start attending these prac sessions where you'll be able to get some MATLAB help, and it's kind of a nice environment to start working on this. At least the first parts of this assignment. Don't be intimidated by the assignment. The last part of it, you're not going to... Does the audio sound weird in here? The last... Can you still hear me okay? The last part of the assignment, you're kind of not going to know how to do that until the back half of this first 6 weeks of the course, okay? So... just some kind of basic bookkeeping for that assignment. It's due by Friday, 16th of September. That date's a little bit arbitrary. I'm just trying to make sure that this potential flow assignment doesn't roll into the compressible flow unit of this course too much. Since that unit's also going to have its own assignment. You're going to be doing the assignment in groups of 2, okay? And both students in the group are going to get the same mark for the assignment. So you've got to start finding team members that you can work with, all right? So choose wisely. You can do the assignment alone. You're not going to be given any kind of dispensation or concession for that. You'll be marked the same as the group assignments, but you can do it on your own. You can't do it in groups of 3, and every year I get plagiarism problems with this group assignment, okay? Just because I'm asking you to do it in groups of 2, there's still such a thing as plagiarism, all right? One group of 2 copying an assignment from another group of 2 is plagiarism. So I understand that you might informally work together in larger groups and that you talk to each other, and indeed I encourage that, but just make sure that there are sufficient differences between those assignments that get handed in. We get problems with this every year when we set group assignments. So choose your partner carefully. I'm not going to listen to any bleeding at the end of semester that your partner went on holiday for 3 weeks and didn't do anything. Only hand in 1 assignment per group. You can use any... I know I keep talking about MATLAB, but you can use any programming language you use. And I know in the instructions I mentioned C and MATLAB, but really whatever tickles your fancy, I just suggest that you seek a numerical solution. And again, I just want to highlight this fact that I'm asking you to write a code to track path lines or to track particles within a fluid flow. And I'm well aware that there are inbuilt functions in MATLAB that can kind of do a half-assed job of this for us. But it's not going to, ultimately, it's not going to work for what we want to do. So don't use Streamline or Contour or ODEXX or any of those other inbuilt functions in MATLAB. Write your own. Obviously, you can use... I'm not saying you can't use any of the inbuilt functions in MATLAB. That would be pointless. Just don't use the ones that explicitly kind of in some way plot path lines. That's not what I'm asking you to do in this assignment. Okay, and yeah, the aim is really to get you to code it for yourself, and I think in doing so you're going to get a better appreciation of the flow fields that we're looking at. And then when you submit that assignment, copies of computer codes, but I also want some kind of proper written report in this case. It at least includes the answers to the questions that you've... I don't need some wordy explanation, but at least the answers to the questions that you've been explicitly asked, and also those computer-generated figures and graphs that you're asked that you're asked to produce. So again, benefit of my experience, a graph without an axis label is just a cartoon, all right? It's got absolutely no engineering value whatsoever. So it's the pet hate of everyone who has to mark assignments. So make sure that you label your figures correctly and make sure that you figure out how to export those figures correctly from whatever programming language you're using, right? Copying, pasting figures into a Word document looks crap, and I think that your end document will look rubbish. You can do better than that. Okay, so question 1 of that assignment is really, really simple, okay? You're given, I'm not sure the numbers are quite correct in this slide, but you're given a simple ordinary differential equation, all right, which is just dx dt equals something. And dx dt is just a velocity, really. It's the u component of velocity. The reason that I'm giving you this as a starting point is it's very, very simple to find an analytical solution to that equation, okay? But we can also use that equation as a, so we could integrate that equation very simply, and we can use those initial conditions that are given to get an analytical solution to that expression, but it's also a useful test bed for you to test out these different schemes for particle tracking or tracking trajectories, okay? So really what that question asks you to do is find an analytical solution and then compare that to a numerical time-stepping solution. And you're going to try an Eulerian scheme, which we spoke about yesterday, and you're going to try a higher order scheme, which is a fourth order Runge-Kutta scheme, which is given to you. Everything you need to know about that fourth order Runge-Kutta or that RK4 scheme is given to you in the assignment sheet, okay? So basically, that Eulerian scheme we spoke about is very, very straightforward, okay? It's just saying that the new position just equals the old position plus the velocity multiplied by the time, right? And you're all familiar with that, or yesterday when your head was in it more, you were nodding to me like you'd seen that equation before in elementary physics courses. So if you think about it, that Eulerian scheme is just a first order scheme, right? It's just saying that as long as I know the gradient of the function at some point in space, I can predict some other point in space from just projecting from that gradient. Okay, so it's a first order scheme, and all that RK4 scheme is, or that fourth order Runge-Kutta scheme, is a higher order scheme. It's saying, well, now if I know the rate of change of the gradient and the gradient at that point in space, I can make a more accurate prediction at some other point in space. And then if I know the rate of change of gradient, I can make an even better prediction. And that's all that fourth order RK4 scheme is. So if you look at that equation, which is given to you in the assignment sheet, it's just saying that the new position is equal to the old position plus some more complicated function of that velocity multiplied by the time step, okay? And you see that K1, K2, K3, and K4 are they're just our original function, but rather than evaluated at the previous time step, they're evaluated at some modification of that previous time step, okay? So actually realizing that numerically is very, very simple. But effectively, when you do that, just know that what you're doing is a higher order, it's a higher order scheme, okay? You're not just assuming that everything's just got linear gradients. You're recognizing the fact that there's a rate of change of gradients and higher order terms in there, okay? So for that simple question 1, you can actually just plot an analytical solution. So there's really no need to use an RK4 or an Eulerian scheme in that case. But the neat thing is that you know what the right answer is, so then you can test that your code is performing correctly, okay? And what you should see on here is that if you plot Eulerian solutions, it will, you know, kind of track that analytical solution, but only if you use a small enough time step, okay? And you'll realize that that Eulerian scheme has a build-up or a propagation of errors involved in it. And the key to minimizing that error is to use smaller time steps. But what's the problem with smaller time steps? Yeah, it's more computationally expensive, okay? So really, I mean, just using ever smaller time steps is going to become very, very expensive for us ultimately. It's even for these solutions we're doing in this assignment, it's going to become expensive to solve them on your laptops, okay? So the alternative is to use that RK4 scheme, and you'll see that it works a little bit nicer. And then the second part of question 1 is just a pair of coupled ODEs, which is just a solution in 2D space. So you're just going to expand those codes that you've developed from 1 dimension into 2 dimensions. And that coupled set of ODEs is really just drawing a closed trajectory in space. Okay, so the analytical solution, it doesn't look exactly like this, but it's something like this. It's a closed solution. And again, we start from some initial conditions. That Eulerian scheme is going to have problems, okay, due to this propagation or build-up of errors, and hopefully I don't feel like I'm giving the game away here too much, right? Your RK4 scheme should work nicer than your Eulerian scheme. So question 1 is a test case. It's going to allow you to prove that or satisfy yourself that your codes that you're producing are working, and then you can go and apply them to some more interesting problems, okay? So just, I would concentrate on question 1 in those, in these help sessions for now. So, question 2 and 3, you're kind of looking or unpacking that smokers problem in a little bit more depth. And there's just one thing that I want to highlight, which I didn't speak about yesterday. So there's a problem, okay? There's a problem where we're representing the extraction fan with a point source, okay? And there's a problem at that point source. Can you remember what it is? It's a singularity, right? So we're violating the conservation equations there, but the problem for us from a coding or a numerical point of view is that the velocities go to infinity when those particles reach that singularity, okay? And you have to trap that somehow within your code. Any numerical scheme is going to blow up when numbers start asymptoting to infinity, okay? So as an example, you know, if I release my particles and I'm infecting them with my Eulerian or my RK4 scheme, the danger is that once they start approaching that source, they're going to start moving very fast, okay? And unless I've got a very small time step, as it approaches that sink, it's going to start moving at very high speeds, and when we impose our time step, it's going to fly out of the other side of that sink. Does that make sense? Where everything should actually just get sucked into and disappear into that sink, it's just going to fly through that sink and then bounce back into it, and we're going to get this very messy kind of streamlined pattern as all these particles just bounce in and out of that sink due to those infinite velocities that happen when we approach that point sink. Does that make sense, what I'm saying? It's kind of like, if you think of it in terms of gravity, it's kind of like that sink is it's like a black hole or something. It has a crazy strong gravitational field, and it pulls, the velocity of everything starts to become really strong when you approach that singularity. Sorry, that was a really shitty analogy. The truth is those particles are just going to bounce in and out of that sink, and it's all numerical error. There's nothing physical about that. So the solution, there's many solutions, all right? But the one that I've been using which I think has been working quite well, is I just, at each of my time steps, I'm just calculating the radial distance of all of my particles from that singularity, from the center of that sink. And when that radial distance becomes too small, I just set those velocities to 0. So this is that kind of logic statement at the top, is saying that if that radial distance rs is less than 0.1, then I'm setting dx dt and dy dt equal to 0. Okay, so that I'm just, once all of my particles get very close to that point sink, I'm just setting the velocity to 0, and then they're all just going to become fixed there. Okay, you can do more clever things. You can just remove those particles from your calculation. That will also solve the problem. But in my case, they just head towards that sink and then just get stuck there, which works pretty well for what we're doing. Okay. Okay, so does anyone have any questions on that assignment, or do you kind of get the ethos of what you're supposed to be doing for those first couple of questions? And as I say, don't panic about question 4, all will become clear in a couple of weeks' time. All right, so back to yesterday's lecture. Where we got to was this very lazy point where we no longer have to look at our governing equations. We've boiled everything down to Helmholtz's equation, and in fact we've made everything even simpler for ourselves. We've just got this expression that says we satisfy all of our governing equations provided that the total rate of change of vorticity is equal to 0. And the solution that we looked at here, the solution that's most useful for us, is since that oncoming vorticity onto most of the flows that we're looking at in this course is going to be 0, Helmholtz's equation is really telling us that the vorticity everywhere within our flow field must be 0. So we've got a flow that is everywhere irrotational. And if we have that condition, we're satisfying those governing equations of motion. So we know that we're satisfying conservation of mass and conservation of momentum. And this is the case primarily that we're going to deal with. So as long as our building block flows are everywhere irrotational, they absolutely satisfy those governing equations. And then moving on from there, this important point yesterday was this realization that, well, if each of our building block flows are truly irrotational, so satisfy Helmholtz's Laplace's equation, then we can simply just add those flows together, safe in the knowledge that that superimposed flow, resulting from that summation of those two flows, still satisfies those governing equations, all right? And this is really, really important. It's all we're going to be doing from this point on in this course, is just adding more and more complicated combinations of building block flows. So for that smoker's problem, I just added the stream function for a source to represent the smokers. I added the stream function for an extraction fan to represent the stream function for a sink to represent the extraction fan. And then all I have to do is add those two stream functions together, and I get an expression for psi for my total flow field for that smoker's problem, all right? And we spoke briefly about how simple that was to code this up in MATLAB and have a quick look-see at the flow, okay? And then finally, this other very important point that we'll be dealing with today, once you have the stream function for that combined flow, you have to be able to work out the velocity components, and that's just a simple, always just a simple differentiation operation. You've got to be able to differentiate that stream function with respect to x and y, okay? So we finished up with this problem, right, that our flow was, it's still wrong. It's still that our flow is permeating the wall, whereas we know that that solid surface or the wall should be impermeable to that flow field. Does anyone, I don't know what your background is, does anyone know the solution to make that wall impermeable? Okay, but I think that those of you who've been through the Melbourne model, there's no reason why you would know. I just thought some lateral entries might know. So the answer is with this, and it's by no means obvious, the answer is to use this method of images, okay? And the method of images is very, very straightforward, and we'll see how it works in just a moment. But basically, the method of images just suggests that if we want a solid boundary anywhere within our flow field, we just make a mirror image of all of those individual flow features below that solid boundary. So the solid boundary becomes the mirror plane within our flow field, and we just generate mirror images of all those building block flows below that. And we'll see that if we do that, it basically ensures that the boundary, that solid boundary, becomes a streamline. And what do we know about the flow along a streamline? What do you know about the flow normal to a streamline? It's 0, right? So if we can make that solid boundary into a streamline, then we can make it impermeable, which is exactly what we want to do in this case, okay? So this method of images is very, very straightforward. If I consider a source that's located some distance ls from where I want my solid boundary to be, if I look at the streamline pattern associated with that source on its own, those streamlines are just straight lines issuing radially outwards from that source. The method of images suggests that all I have to do is add another source, a distance ls below where I want that solid boundary to be. So just make a mirror image of it. And then my stream function for that total flow field just becomes the stream function for the source plus the stream function for that image source. And you'll see that we get exactly what we want out of this summed flow. If you now plot the streamline pattern, which remember are just lines of constant stream function, if you now plot the streamline pattern associated with this mirrored arrangement, you can immediately get some sense that those streamlines are no longer penetrating through that solid boundary, okay? And so this is kind of weird, right? In this particular example, I'm placing a flow feature below the floor. So I'm placing a flow feature somewhere where in my model there is no flow, all right? So that flow beneath the wall is kind of imaginary, all right? Those streamlines below the wall we kind of never want to look at because we're going to model that as a solid boundary. When I say imaginary, I don't mean in the mathematical sense that it's got a real and imaginary part. I mean it's kind of make-believe, okay? We're just putting it there to satisfy, we're putting that feature there to satisfy a boundary condition. So you could plot streamlines below the wall, which I'm showing here in these dashed lines, but that's kind of moot because we're never going to look at there is no flow below the wall. We're considering that it's there's no fluid there. It's a solid boundary. So we can see what makes this tick actually by just computing the horizontal and vertical components of velocity. So all I've got to do to calculate the u component is just differentiate that stream function, which is the source summed with the image. I've just got to differentiate that with respect to y, okay? So again, you're going to get good at differentiating arctans, but all I've got to do is differentiate that bracketed arctan term with respect to y, which, as long as I'm careful, I should be able to do. Okay, so we can get an expression for the horizontal component of velocity from this, and we can also get a component for the vertical component of velocity by so in this case, I have to multiply the stream function psi by -1, and then I differentiate with respect to x. Does this make sense to everyone? How to get those velocity components? Those of you who aren't asleep, does it make sense to you? So it's okay. I'd also like to go to sleep myself, but I'm contractually obliged not to. All right. So when we do that differentiation, we'll get an equation for the vertical component of velocity v. All right? So what we can do is now, so where's the wall located in terms of x and y locations? What do I know at the wall? How can I describe the wall? Y equals 0, right? So I can substitute y equals 0 into these expressions. So consider that vertical component of velocity and let y equals 0. Okay, so y equals 0 is the line of the wall shown by that red dot dash line. And if I set y equals to 0, you get this happy result that you should be able to see that that term within that square bracket just cancels to 0. And what we've got is that vertical component of velocity is identically equal to 0 everywhere along that solid boundary. Okay, so there's no vertical component of velocity where we want our wall to be. So we've got an impermeable boundary, which is exactly what we want. And we might have guessed that by just looking at the streamlined pattern that I plotted. And that's basically how that method of images works. By having by making an image of these flow features, we impose a plane of symmetry, all right, effectively. And that plane of symmetry, in this case, we're calling our wall, and we know that on that plane of symmetry there's going to be no flow normal to it. So it's a useful result if we want to impose solid boundaries. If we look at that horizontal component, things are a little bit more complicated, okay? So again, I can put y equals 0. I can let y equals 0 in this expression, which will simplify down to this equation here. So this expression now is the variation of the horizontal component of velocity along the wall, along that y equals 0 line. And you can see that the velocity u doesn't equal 0, okay? It only actually equals 0 that equation simplifies down to this form here, but it only equals 0 when x is equal 0, all right? Is that obvious to you by staring at that? You can see that from that expression. So I guess this has nothing to do with images, but it's a concept that we have to get used to. So that position x and y equals 0 is now a unique point in our flow, right? So at that origin 0, 0, both v and u are equal to 0, and this is known as a stagnation point, and it's quite obvious why we call it that. The flow absolutely comes to rest at that point 0, 0. So if I released a particle of smoke at that origin, it wouldn't go anywhere, right? It's just going to remain there. And stagnation points occur in real physical flows, and we'll talk about them more in this compressible flow course. But for now, they're very, very useful for us. Actually, the key to if we don't have a computer lying around, the key to understanding these flows is really to map out where all of these stagnation points are located. And then we can, just with a pen and paper, we can fully sketch these flow patterns and understand what makes them tick. So there's a stagnation point at 0, 0, but everywhere else, u has some finite value along the wall. So what's the problem with that? So that solid wall it's impermeable in terms of the wall normal component, so it's impermeable, but the horizontal component of velocity isn't 0 other than at that stagnation point. So that's a little bit problematic, right? What do you know about the velocity at solid boundaries in the real world? There's a no slip, right? But we've thrown that out. In our laziness, we tossed out the no slip condition with all of those viscous terms from the Navier-Stokes equation. So it's an important point that we've got slip at the solid boundaries in this case, okay? And that's just that's an artifact of these simplifying assumptions that we've made. So again, the flow that we're modeling here, very close to those solid boundaries where we'd expect those boundary layers to be as a result of those no-slip conditions, our modeled flows wouldn't be expected to be particularly accurate in those locations, okay? So anyway, that's an aside, or just we need to remember these things because we need to remember the limitations of potential flow, especially when you go out and practice as engineers. So another definition is that so we've defined that stagnation point where U and V are equal to 0, and we also define the streamlines that pass through that stagnation point as lines of separatrix, so we call them separatrix lines. And again, that name is pretty obvious because those streamlines that pass through the stagnation points actually demarcate or separate one part of the flow field from another. Okay, so any flow, no flow below that solid boundary can ever reach above that solid boundary. Nothing can pass through those lines of separatrix. So again, coupled with the stagnation point, knowing where those stagnation streamlines are is really, really important in terms of understanding the topology or the shape of the flow field that we're dealing with. Okay, so at the moment, for that smoker's problem, we've only got a floor, okay? So the problem of images is pretty straightforward. If we were trying to model rooms, things become a little bit more difficult, okay? So I could, if I had a source that was kind of equidistant between the floor and a ceiling, I could add an image source about the floor and the ceiling, and I could write out my stream function for these 3 building block flows, all right? Which is my original source plus the image on the bottom plus the image on the top. But when you write out the velocity equation for that set of 3 sources, what you'd realize is that the velocity at y equals 0, which is at the bottom wall, doesn't equal 0, okay? Can anybody tell me what I've done wrong by applying the method of images in this case?
The mirrors are half as strong as they should be half as strong.
Not quite. I think you're on the right lines, but I might be being kind. But it's kind of like this. It's kind of like this infinity mirror. Okay, that image source at the top, the image right at the top reflects in the bottom wall. So there should be another source image somewhere down there, and then that one reflects in the top wall. So there should be another image at the top, and kind of so on to infinity, okay? So what I really, with those 3 features, my streamlines penetrate those walls. What I really need to do is add all of those images, okay? So there's another image down here, and if I add that one, I do get 0 flow at that bottom wall, but I've got non-zero flow. I've got non-zero flow now at the top wall. So there's non-zero flow now at the top wall, so I need to add more and more of those reflected images, okay? And if you keep doing that, the flow eventually converges to the solution, which is an impermeability condition at that top and bottom wall. So it's really just like this. It's really just like this kind of infinity mirror, which you've all probably seen before. So infinity is pretty useless in terms of computational modeling, but I would say in this case, I only needed to add, 4 or 5 reflections before I had a solution that was certainly good enough for government work, okay? So you don't need to keep adding infinite numbers of reflected sources. All right, anyway, back to that smoker's problem. So we've got a source, the smokers are a source, we've got a sink for the extraction fan. Now what I've got to do is add a mirrored, an image source below the smokers and an image sink below the smokers. So now my stream function is made up of the original source and sink plus that image source and sink for which I'm using sub I, or actually I'm just showing it in red to remind me that they're the images. So now my equation for the stream function is made up of 4 features, right? The real source and sink due to the smokers and the extraction fan and their imaginary counterparts, which I'm showing here in red. Does that make sense? I mean, I know it's not pretty algebra. That equation looks like it's starting to look intimidating, but actually it's still very, very simple to do all the operations that we need on that expression. So if I now plot lines of equipotential or streamlines, you can see that I've satisfied that impermeability condition and everything is looking a little bit better, okay? So we're no longer permeating the wall, but in this case, which is where this is quite a foolish case actually, right? At the moment in my solution, I've set the strength of the source equal to the strength of the sink. So that means my extraction fan is sucking at exactly the same rate that the smokers are blowing, which is, you know, pretty unrealistic, right? I mean, you'd have to be quite an enthusiastic smoker to blow smoke at the same rate as an extraction fan. But anyway, you know, these are times where we're trying to save energy and make efficient buildings. So I guess someone could be that stupid. So at the moment, QE on QS. The strength of the extraction fan, QE on QS equals 1, so strength of the extraction fan and the smokers is equal. And the non-smoker dies, all right, because the smoke permeates everywhere within this flow field, all right? So, but what you should see, or actually we'll show this algebraically in just a second, but what you'll see is that the shape of the flow field or the topology of the flow field is heavily dependent on that ratio QE on QS. So if I start to kind of increase that ratio, so I'm now making the extraction fan stronger than the smokers, the red lines on here show lines of separatrix, okay? And you'll see that as I increase the strength of the extraction fan, I can actually move that line of separatrix inwards, so I can contain that smoke within some finite area, which we can then keep the non-smokers out of, okay? So just as an example, we kind of looked at this. I'm not sure on the number here, but we looked at this in yesterday's lecture. So now I've got the images in here, so none of my particles are penetrating the wall. And here the ratio is 1.8, and you can see that we're kind of stopping the smoke. We're stopping that smoke from reaching the, actually stopping most of that smoke from reaching the non-smoker, okay? I think he still gets it in the end, but if I'm almost there, right? If I just increase the extraction fan a little bit, everything would work. Okay, so let's look at this algebraically and look why that should be the case. So what I want to do is write out expressions for the horizontal and the vertical component of velocity u and v, all right? So for u, I've got to differentiate that stream function psi with respect to y, all right? So again, I've just got to differentiate those arctan terms with respect to y, and I get this beautiful expression for the horizontal component of velocity shown at the bottom. And there's not much I can do to clean that up, okay? I can gather the terms that are multiplied by QS and QE together, okay? But it's, you know, it's kind of like polishing a turd. It's still going to be this very long algebraic expression, but we can simplify it very nicely for ourselves in a moment. And we can do the same thing with that vertical component of velocity. Multiply the stream function by -1 differentiate that equation for the negative stream function with respect to x, and we get an equation for that vertical component of velocity. And again, we can gather those terms involving qs and qe together. So all you need to know is if we've got an equation for the stream function, we can get an equation for the velocity components u and v, okay? So the key to understanding what makes this flow tick is to find the stagnation points, okay? So, and you know, and the stagnation points are just a solution to that simultaneous set of equations, okay? I know that stagnation points occur when u and v are both equal to 0, okay? So I could just set both of those equations equal to 0 and try to solve those as a set of simultaneous equations. It's actually often simpler to be a little bit more clever about it. There's often a simpler solution that's staring us in the face, okay? So in this case, if we take the equation for the vertical component of velocity, I know that vertical component of velocity is everywhere 0 along the wall, okay? Because I've put those images there. I've created an impermeable boundary. So I know that at y equals 0, v is everywhere equal to 0. So if I just let y equal 0, that equation for v reduces to this expression here. And if you stare at it for long enough, you can see that equation reduces to 0. All right? So I know v's everywhere 0 along the wall. So now all I have to do is look at the equation for u and see if u is 0 at any points along that wall. Okay? So we just take that equation for the So what I'm showing here is that I immediately know that I've got a separatrix, a horizontal separatrix, where that solid boundary is. But we kind of knew that anyway. That was the whole point of us putting the image features in the flow, those reflected features. So now all I've got to do is substitute y equals 0 into my equation for the horizontal component of velocity, that equation for u, and then solve that for x locations where u is going to be equal to 0. So I just substitute. Does everybody understand that? So I substitute y equals 0 into that equation, and now what I've got is an equation for the variation of the horizontal component of velocity along my solid boundary. Okay, and you can see that equation kind of tidies up a little bit for us. Okay, so at the stagnation points, I know that u's got to equal 0. All right, so I can just set u equals to 0 and rearrange this as this simple equality. So one stagnation point staring us in the face, right? Right? So you can see that when x is equal to, I've changed x to xs now because I'm trying to solve this for the x locations of the stagnation points on that y equals 0 line, okay? So one solution's obvious. When x is equal to 0, I'm going to satisfy that equality. So I know I've got a stagnation point at x equals 0. That was also pretty obvious from just staring at the flow field, okay? We know there's going to be a stagnation point on that line of symmetry, on that horizontal line of symmetry where all of those sources and sinks lie. Let me just back up a second, all right? So that stagnation, use the pointer rather than making an idiot of myself, all right? So that's this stagnation point here at x equals 0, and we know that there's going to be a vertical separatrix, which I'm showing with this red line running through that point. Okay, so we've got 1 at x equals 0, and then all we've got to do is rearrange this equation and solve it for those other x locations, all right? So actually all I've got to do is invert that equality. So just 1 divided by the left-hand side of that equation is equal to 1 divided by the right-hand side of that equation, and we'll get to this expression shown at the top here. And if I just multiply that out and gather all the x all the terms involving excess squared together, I can very simply solve it. Okay, so excess squared is just going to be this minus this bracketed term here divided by this bracketed term here. Okay, so I get an expression for excess squared, and obviously excess is just equal to plus or minus the square root of that expression. So I'm probably kind of moving through that algebra pretty quickly, but there's nothing other than the fact that it's Friday afternoon and I'm going a little bit quickly. There's nothing complicated there, right? There's nothing mathematically that ought to intimidate you. There's very simple linear equations. As long as we can differentiate an arctan, and as long as we can rearrange some very simple expressions, we can get an equation for where those stagnation points are located, okay? And that expression, I think, is really key, okay? It tells us the bounding limits of this smoker's problem that we set up, all right? So if you stare at that expression for long enough, we know that LE, which is the height of the extraction fan above the floor, is greater than LS. Okay, so the extraction fan in my sketch is above the smokers, so we know that that's the case. So you can see that that solution is entirely dependent on that ratio QE on QS, which is the strength of the extraction fan relative to the strength of the smokers. And what you should see is that if QE on QS is less than or equal to 1, there is no real solution to that equation, all right? And by, algebraically, that's very easy to see, right? If QE on QS is less than 1, this term on the bottom is going to be negative, this term on the top is still going to be positive, and we're going to be taking a square root of a negative number, which is going to have no real solutions, all right? So, and no real solutions in this case means that there's going to be no stagnation points in that flow other than the stagnation point that we've already found at x equals y equals 0, okay? And then physically it's obvious too, because QE on QS less than 1 is that the smokers are blowing smoke harder than the extraction fan is sucking, which intuitively we might think wouldn't work, okay? So in that case, there's no separatrix and no safety zone for the non-smokers. So airport or whatever the building that we're considering is going to be entirely permeated by smoke eventually, if that's the case. If QE on QS is greater than 1, there is a real solution as given by that equation at the top there, okay? So in that case, there are another 2 stagnation points at plus and minus XS, and those 2 stagnation points are going to define this separatrix, which is going to contain that smoke around the smokers, all right? Does that make sense? So that equation gives me XS, and that gives me a plus or minus XS, which is a stagnation point location along that horizontal wall, okay? So it's just telling me that there's going to be a stagnation point here and a stagnation point here. There's going to be a separatrix passing through that stagnation point, which means that the smoke from the smokers is going to be entirely contained within that region, which you would have seen from that MATLAB movie that I showed previously. Okay, so the extraction fan, somewhat obviously, has to be stronger than the smokers. Okay, so I'm probably I'm running out of time once more, but so I'll finish here. All right, but that. For all of these solutions that we seek in incompressible irrotational flow, those stagnation points are always going to be saddle points, all right? Which means that you've got flow coming into that stagnation point in one direction, and you've got flow flowing out of that stagnation point in another direction, okay? And that's always going to be the flow topology that occurs at those stagnation points. So for any I know this smoker's flow, I've been kind of showing you what it looks like as we go along, but any flow that we might choose to build by adding building block flows together, the key to understanding what the streamline pattern or the flow topology is going to look like without resorting to a computational model is to solve those equations to find where those stagnation points are located. And once we know where those stagnation points are located in physical space, we know that each of those stagnation points is a saddle node. And once we draw in those saddle nodes, we know the shape of the flow field at those particular points. And then by just connecting those stagnation points together, we should be able to sketch out that flow field straight away without having to resort to a computational model. And we'll get plenty of practice of this through your tutorial questions and as we move on through this course. But defining those stagnation points and those lines of separation, lines of separatrix are really key to potential flow solutions. Do you understand that? It was key to that smoker's problem. If we didn't know where the stagnation points are, we didn't know where the non-smokers should be located. So there's more stagnation points in that problem, but luckily for you, I'm out of time, and we can save that torture for Tuesday's lecture. Okay.
Excuse me, sir. Yesterday I was looking for the elections this week, but I didn't find them.
I think I haven't put them. I haven't put them up yet.
Oh, yeah, okay.
So I'll try and get them up as soon as I can now, so that you guys can.
Because I told you that it was a problem with me because I didn't find them. Because I always said so.
It's a problem with me. I'll try and get them up there as soon as I can.
Thank you. Just in terms of like extraction and Q source, is that just a measure of intensity?
Yes, it's actually truly a volume. It's a volume program.
Yeah. Okay.
So that if I set that value to 1, it means I'm sucking 1 cubic meter per hair per second.
Yeah. Okay.
Yeah. So I mean, from a modelling point of view, we need to know roughly what that, I guess
what it's going to be.
Yeah.
So when tutorial questions come around, it won't all just be algebraic. There'll be some actual numbers to sub in.
There should be, but
when I can see the units, it helps me understand. That's pretty good.
But on that note, I guess the assignment question, the numbers.
Yeah. I mean, it's much more useful to know it algebraically.
I think so, but I'd say maybe that you made me realise that the numbers I've given for QS for that assignment question would be some pretty vigorous smoking. 1 cubic meter.
Maybe it's one of those rooms with people sitting
Yeah.
around. It's just a whole thing.
I think that's what I have in mind. I mean, if you've ever flown through Singapore, I mean, some of them are in contained rooms, but I've even seen ones where there's just people stood under these crazy
Or they just have a designated area and everyone just crams under there. So you could almost treat it as a point source.
I think so. And so you've got really strong extraction, and you don't even need the horrible glass room around it. In theory.
Yeah, no, that's
Okay.
makes sense. Thanks.
In my timetable, there are 2 practicals. I don't know which practical do we need to come next week.
It's the one that's in the. It's prac 1 next week. So prac 2 is the laboratory. You only go to one of those through the whole semester. Prac 2.
Practical 2.
Sorry, prac 1 is the MATLAB help sessions, which you're going to go to from week 3 to week 5.
Okay.
Prac 2 is the laboratory. You just go to one of those throughout the whole semester. Right?
Then which time do we need? Because once we select the time, we can no longer check which time is this, the 7th section. I don't know.
So did you sign up for a laboratory?
Where can we sign up?
In your student portal? I mean, you know how you sign up for tutorials and
Yeah.
So did you sign up for prac 2?
Yeah.
Yeah, so you would have signed up to a particular date
Yeah,
and a particular time.
but if we forgot that